Last class we were discussing the reactions of alkanes. As you know, alkanes are normally are not highly reactive, and halogenation reaction is one of the reactions that normally alkanes can provide. And the chlorination reactions we have already discussed, and due to some technical issues this slide has not been shown yesterday. This slide details about the bromination reaction of alkenes. As you know, chlorine is more reactive than bromine, so chlorination reaction can take place more readily as compared to bromine, even at very rigorous conditions. So when you want to do the bromination reaction, you have to give more rigorous condition. Okay. So this reaction is taking place in the presence of UV light or at a very high temperature, 250 to 400 degrees centigrade, to yield the bromo derivative of alkenes. The reaction occurs in a manner similar to that of chlorination, but only less readily. Okay. So here the reaction scheme is shown. Methane is reacting with bromine in the presence of UV light or heat at high temperature. Then we get bromomethane, CH3Br. Okay, so when we take an example of ethane reacting with the bromine at UV in the presence of UV light or at a high temperature heating, then we get bromoethane, CH3CH2Br. And with excess of bromine present, further substitution of the hydrogen atom by bromine atoms occurs. As you know, we have already discussed the more chlorinations in stepwise manner. If more chlorine is present in the system, more hydrogens will be replaced by chlorine. So similarly here also, if excess bromine is present, the hydrogens will be subsequently removed by or substituted by bromine. Next we are coming to alkenes. As you know, alkenes, enes, carbon-carbon double bonds are there, will be present in the hydrocarbon chain. So as you know, a carbon-carbon double bond will be seen in the reaction system is what is called in the compound is called alkene. Here the general formula for the representation of alkenes is CnH2n. Alkanes it was CnH2n plus 2, and that plus 2 has removed here. Here 2 hydrogen atoms will be less, because if n is 2, then if 2 carbon atoms are there, n is 2 means 2 carbon atoms are there, then this will be H2 into 2, 4 hydrogens will be there. For example, ethylene is given 2 carbons are there, and there will be 4 hydrogens. Okay. If n is 3, H will be 2 into 3, that will be 6. Okay. For example, propylene 1, 2, 3 carbons are there, and then we have 3 plus 2, 5 plus 1, 6 hydrogens. Okay. Now these alkenes show structural isomerism for higher alkenes. Structural isomerism in the sense it can give chain isomerism as well as structural chain as well as position isomerism. Okay, so these two are actually the structural isomerism. So will be discussed later. Now let us discuss the nomenclature of alkenes. So the nomenclature of alkenes in the sense, as we have already discussed in case of alkanes, so we have to count the longest hydrocarbon first. Okay, and then we have to find out where the carbon-carbon double bond is present in the molecule, and then we have to give the number in such a way that the carbon-carbon double bonded carbon should get the least number. Okay, then in certain cases higher alkenes there will be substituents present, and then we have to in the numbering system we have to specify the substituent present on the carbon atom. And if 2 substituents of the same kind is present on different carbon atoms or same carbon atom, then we can use the word di, tri, etc. Okay, and then if 2 different substituents are present like methyl, ethyl, then which comes alphabetically first has to be mentioned, and then the second comes in the alphabetic should be mentioned. Okay, so this is exactly what we had seen in alkenes, but here only difference is wherever the carbon-carbon double bond comes, it should get the least numbering, and then the substituents has to be in alphabetic order if different substituents are there. Okay. For example, if we take CH2 double bond CH2, that is ethylene or ethene, so there is no need to give an IUPAC naming. Here it is CH3 CH double bond CH2 propylene or propene, and here also we don't need to give an IUPAC naming. But in this case we have to give IUPAC name CH3 CH2 CH double bond CH2, because carbon-carbon double bond can be either on the N carbon atoms or at the second and third carbon atoms. Okay, so these two compounds molecules will be different. So here we have to specify where the carbon-carbon double bond is present. Okay, so here the first carbon atom, carbon-carbon double bond is present. Okay, so we have to specify this is butane 1 2 3 4 buta. So this is but 1 ene, one carbon atom, double bond is there, ene, ene. Always the name ends with ene, ene. Or otherwise it is called, previously it was called 1 butene. And in this case the same compound, but the carbon-carbon double bond is present between 2 and 3. Here it is what is called but 2 ene or 2 butene. And in this case this is little more higher alkene. So in this case we have a substituent here, so we have to find out which is the longest hydrocarbon chain. 1 2 3 4 5 carbon atoms are there, and carbon-carbon double bond is present between 2 and 3, so we have to specifically mention 2 ene. Okay, so here 4 carbon atom, there is a methyl group present, 4 methyl pent, 5 carbon atoms are there, pent 2 ene. Okay, so now let us discuss the another example. CH3 CH CH3 CH double bond CH CH CH2 CH3 CH3. Okay, so in this case the longest carbon hydrocarbon chain is, if we number like this only. Okay, we cannot number like this because this is the longest hydrocarbon chain, so this methyl group is a substituent. Okay, so there are 2 methyl groups as the substituents on the second carbon atom and also on the 5th carbon atom. Okay, and so here this is 2 5 dimethyl, 2 methyl groups are there, so that is dimethyl hept 3 ene. Okay, 7 carbon atoms are there, that is hepta, and then hept 3, third carbon atom, carbon-carbon double bond is there, 3 ene. And if we take another example, CH3 CH2 CH, the number of carbons in the parent hydrocarbon chain is 6, and second carbon atom CH3 group is there, and fourth carbon atom C2H5 group is there. Okay, so we have to first mention the ethyl group, and that is 4 ethyl and then 2 methyl hex 1 ene. Okay, so it is easy, so you have to look at different examples and then write down the names. And now let us discuss the other 2 examples too. Here there are 3 third carbon atom, 2 CH3 groups are there, and 5th carbon atom another CH3 group, so 3 3 5 trimethyl. Okay, so that is the name of the compound, 3 3 5 trimethyl hex 1 ene. Okay, so in this case we have 7 carbon atoms are there, so that is hepta, and then 3 third carbon atom, carbon-carbon double bond is present, and 2 methyl groups, these 2 are yeah, in fact this compound and this compound is the same. Okay, anyway, now if we take this example, ethyl and methyl group is there, so you can give the naming, and here also we have 3 CH3 groups are there, so you can give the naming. So this example and this example is same. Okay, all right, so let us discuss this one. Okay, so here we have second carbon atom, 1 CH3 group is there, and this one ethyl group, methyl group, methyl group, methyl group. So first we have to mention the on which carbon atom the ethyl group is present. So this is 4 ethyl, then 4 C3 groups are there, so 2 4 5 5 tetramethyl hex 1 ene. Okay, now let us discuss the structural isomerism in alkenes. Alkenes exhibit structural isomerism, or particularly higher alkenes exhibit structural isomerism. Structural isomerism can be of chain isomerism and also position isomerism. Okay, for example, if we have a compound with the molecular formula C4H8. We have three different structures. One is CH3, CH2, CH double bond, CH2, butane, and then CH3, CH double bond, CH3, butene. Okay, and then another one CH2 double bond C, CH3, CH3, 2-methyl propene. Okay, so in this case, the position of the carbon-carbon double bond is different, but the structure is exactly same. Okay, so in that case, structure is same and the position is of the double bond is only different. That is what is called the position isomerism. Okay, and so in this case, we have two position isomerism. This and only one position isomerism. A and B are position isomers. Examples for position isomerism. Okay, and in this case, when we compare this compound with this compound or this compound, structurally these two are different. Okay, so A and C are example for chain isomerism. Okay, its chain is different, hydrocarbon chain is different. So A and C are example for chain isomerism. B and C are different. So these two are chain isomerism. Okay. Now let us discuss with another examples. We have C5H10 is the molecular formula, and then we have different structures possible A, B, C, D, E. Okay. So in this case, this structure and this structure, A and B structures are same, but the position of the carbon-carbon double bond is different. So A and B are examples for position isomerism. Okay. But in this case, C, D, and E, in these three cases, its structure is same, but the carbon-carbon double bond position is different. So compared to C and D are examples for position isomerism. C and D example for position isomerism, and these are examples for position isomerism. Okay, and then compared to this and this structure, the chain, hydrocarbon chain is different. So A and C are example for chain isomerism. A and D, B and C, B and D, and B and D are also example for chain isomerism. Okay, now let us discuss the preparation of alkenes. Alkenes are normally prepared by the elimination reaction, particularly by the beta elimination reaction. So this type of reactions result in the introduction of a double bond into a substrate molecule, are widely used for synthesis of alkene. It is one type of elimination reaction in which the two atoms or groups lost in the process. The elimination reaction means two atoms or groups are lost from the adjacent carbon atoms of a substrate molecule. Okay, so if two groups or atoms are lost from the adjacent carbon atoms only, there will be formation of a carbon-carbon double bond. Okay, and an elimination reaction is one in which substrate molecule loses two atoms or groups from the same carbon atom. Same carbon atom is called alpha elimination, or adjacent carbon atoms what is called beta elimination under the influence of an attacking reagent. Okay, so an attacking reagent should be there, and under the influence of this attacking reagent, the elimination of the groups or atoms are taking place from the adjacent carbon atoms, then we will get alkene. First reaction, let us discuss. This is the dehydrohalogenation of alkyl halide. So when you take an example of alkyl halide, then the possibility for a dehydrohalogenation, one hydrogen atom and one halogen atom will be eliminated as the beta elimination reaction under the influence of a base. Okay, so the elimination reaction involving the removal of proton and a halide ion from an alkyl halide. Alkyl halide, as you know, are CH2Cl. Under the influence of a base to yield an alkene is called dehydrohalogenation. The word itself indicates that dehydrohalogenation, hydrogen and halogen is removed, dehydrohalogenation. Okay, the base bringing about the reaction is often a strongly basic anion like hydroxide, ethoxide, tertiary butoxide, etc. But in certain cases, the solvent itself, for example, a neutral substance like alcohol or water, sometimes serve as the base, although it is a considerably weaker base as compared to hydroxide or alkoxide. So in the presence of ethoxide or alkoxide, definitely the reaction will take place, because they are the strong bases. But in certain cases, even the weak bases can also bring the reaction, bring out the reaction. So now let us discuss certain examples. When ethyl bromide, it is otherwise called bromethane, is heated at with the hot concentrated alcoholic KOH. Alcoholic KOH is, you have to keep it in your mind, alcoholic KOH is used for the dehydrohalogenation reaction. Okay. So we have ethyl bromide CH3 CH2Br is reacting with alcohol OH minus. It is provided by alcoholic potassium hydroxide, and on heating the dehydrohalogenation is taking place. One hydrogen from here and one bromine from here is eliminated as HBr, and then we are getting ethylene CH2 double bond CH2. So second reaction, second example is when isopropyl bromide. So we have isopropyl bromide CH3 CH CH3Br. Okay. So this is reacting with the alcoholic KOH, then we are getting propylene. Okay. So here what happens is one hydrogen from here and one halogen from here is eliminated. So adjacent carbon atom, this is beta elimination or dehydrohalogenation reaction. Okay, then we are getting propylene. And if you take another example, tertiary butyl bromide as an example, reacting with ethoxide and heating, then one halogen from here and one hydrogen from here is eliminated, and then we get CH3 CH3 double bond CH2 2-methyl propene. In some cases, dehydrohalogenation of alkyl halides may yield a mixture of isomeric alkene. Okay, so that depends on the structure of the alkyl halide. Depending on the structure of the alkyl halide, there are possibility for a mixture of alkenes, formation of different alkenes, possibility of the formation of different alkenes. Okay, so in those cases, the predominant product can be predicted with the help of a rule called Zaitsev rule. You might have studied it, Zaitsev rule or Zaitsev rule. It was introduced in 1875, commonly called as Zaitsev rule. For example, we have taken 2-bromobutane CH3 CH2 CHBr CH3 in the presence of alcoholic potassium hydroxide. There are two possibilities here, either the hydrogen from this carbon atom or the hydrogen from this carbon atom can be eliminated. But so if hydrogen removed from this carbon atom, we get one product, and if we hydrogen removed from this carbon atom, we get another product. Okay, so here if hydrogen is removed from this carbon atom, we get this product but2-ene, and if hydrogen removed from this carbon atom, we get the second product. But the first product, so we are getting a mixture of product, but the first product but2-ene is the major product. Okay, so this is 81% yield. Okay, but this is the minor product, this is just 19% yield. Now Zaitsev rule, what Zaitsev rule says? Alexander Mikhailovich Zaitsev, that's what the name of the scientist, Alexander Mikhailovich Zaitsev. So Zaitsev rule says that the alkene formed in greatest amount, the product alkene is formed. Which one is the predominant one? That is what the discussion is. Okay, so is the one that corresponds to the removal of hydrogen from the beta carbon having the fewest hydrogen substituent. So here it says that alpha carbon is the carbon where the leaving group is attached. Okay, so here leaving group is bromine, so this carbon is alpha carbon, another carbon is the beta carbon. So here we have two beta carbons, this is beta carbon and this is also beta carbon. Okay, so he says that the hydrogen from the beta carbon having the fewest hydrogen substituents. So in this case, on which beta carbon the fewest number of hydrogens are there, okay, then that hydrogen atom will be eliminated and that product will be the major product. Okay, so when you look at this compound, here we have only this beta carbon only we have 2 hydrogens, and this beta carbon we have 3 hydrogens. The